These are the day 3 notes for our confidence intervals unit. Today we're going to look a little bit more deeply at margin of error, standard error, and a new type of interval called the one sample t interval. So let's go back and take a look at this interval we've talked about the last 2 days in class, which is the one sample z interval for means. We have our formula here, x bar plus or minus z star times sigma over the square root of n. We brought up margin of error when we started the unit, and the margin of error is part of this formula. It's essentially the stuff after the plus or minus sign in a confidence interval. So it's this z star times sigma over square root of n piece of the one sample z interval formula. So it's just this stuff. It does not include the plus or minus sign. It's just the z star times sigma over square root of n. That's the margin of error. So if you're asked to calculate it, that's what we crunch out. There are 3 ways we've talked about to reduce the margin of error in this type of problem. The first thing that we can do is we can make z star smaller by reducing the confidence level. This gets a frown. Ideally, it's nice to reduce the margin of error, but we also don't want to make that happen by reducing our confidence. We want to be very confident in our answer. So one thing we can do is make z star smaller in this formula. That's usually not something we want to do. So let's look at sigma. We could make sigma smaller as well. That's our population standard deviation. Usually to make sigma smaller, what that would require would be removing data points, especially points that are outliers. That's usually kind of a sticky situation too. We usually don't want to eliminate data points. Some people might view that as being kind of sketchy. So option number 3 is to make this margin of error smaller. We could increase the denominator. That's your sample size. And this is usually our best idea. The best way to reduce the margin of error is increase the sample size. And in most experiments we do in math class and statistics, that's usually kind of the option we want to go with. Reducing the margin of error behaves the same way that standard deviation did in our last unit. The idea is square this denominator. So if we want to reduce the margin of error to half its size, square the bottom there. We're going to multiply n by 4. If we want to reduce the margin of error to a quarter of its size, again, we've got a 4 that we're going to get in the denominator by square rooting the number 16. So we'd multiply your sample size by 16. And if we want to reduce the margin of error to a tenth of its size, to get a 10 down here in the denominator, think of what would you have to square root to get the number 10? 100. So we'd multiply the sample size by 100. Again, basic idea here is square whatever the denominator is. That's what you would need to multiply your sample size by. So we just got done talking about what margin of error is. There's another measurement that we can also look at, which is called standard error. Now in our formula for our confidence interval, we have all this stuff going on here. The margin of error is the stuff after the plus or minus sign in a confidence interval. If we ignore the z star and just focus on this last piece, the sigma over the square root of n, the stuff after z star is the standard error. So you'll notice I also wrote here the stuff after z star or t star. There are future confidence intervals where we're going to substitute a value called t star in. So the stuff that is after this particular value, it's either after z star or t star in a confidence interval, is called the standard error. In the confidence interval we're looking at, or we looked at in the past, the standard error would be found by just taking sigma over the square root of n. So margin of error is everything after the plus or minus sign. Standard error is just the stuff after t star or z star. So we just talked about t star, and t star is used in something called a one sample t interval for means, which we're introducing today. When do we use a one sample t interval for means? Pretty easy answer here. It's very similar to the last confidence interval we worked with, but we use a one sample t interval when we don't know sigma. So if we don't know the population standard deviation, but it's kind of a similar situation. We're trying to predict something about the mean of the population, but we don't know sigma, that's when we'll use a one sample t interval. So we're going to use the one sample t interval when we don't know sigma, but we still want to estimate the mean of the population. So if we know sigma, use a one sample z interval. If we don't know sigma, use a one sample t interval. The formula for a one sample t interval is very similar to the formula for a one sample z interval. We're still going to start with x bar plus or minus. Now we're going to use t star instead of z star times s over the square root of n. So very similar formula to what we had before. Again, we're replacing the t star here with what used to be z star. And we're going to use s, which is the sample standard deviation. Remember, if you use 1var stats on your calculator, if you have data on your calculator, you can find both x bar and s using the 1var stats feature. So setting up a one sample t interval problem is going to be almost exactly the same as setting up a one sample z interval problem. There's only a couple things that are different. In step 1, the name of the procedure is a one sample t interval instead of a one sample z interval. And then the formula in step 3 is going to be this new formula. So we're going to have an s value to plug in, sample standard deviation, which you can get on your calculator. And then there's this t value t star, which we'll talk about on the back side of your worksheet. This is going to use this table B that we talked about the last couple days, but we're going to be using something different in table B today.